Okay, so maybe we can start. Hello, everyone. Good morning, good afternoon, good evening, wherever you are in this globe. So I'm Eleni Diamati from Sorbonne University in Paris. I'm very, very happy to chair the next session, which is one of the famous QCrypt tutorials. We're extremely happy to host, to hear Charles Lim from the Department of Electrical and Computer Engineering in National University of Singapore and the Center for Quantum Technologies of Singapore. Hello, Charles, and Charles is going to talk to us about the security analysis of practical QKD. Before Charles starts his presentation, I would like to remind everyone that you can ask your questions through the QCrypt Slack channel, the dedicated channel to Charles' tutorial. And it will also be possible, this can happen during the presentation, and I'll try to relay in appropriate times to Charles your questions. And then at the end of the presentation, there will be sufficient time for some of the participants to ask their questions as well in person. So I will unmute you if you would like to ask some question to Charles. And you will be able, I think, to meet also Charles after the presentation in the dedicated area in the Meet Anyway platform. Okay, thank you very much, Charles. I'll let you speak.
Sure. Thank you, Eleni, for the very nice introduction. So I just want to do a quick check. You guys are able to see my cursor and the screen, right? And able to hear me?
Yes, yes.
Okay, very good. Yeah, so, when the steering committee sort of, invited me to give a tutorial on the practical security of QKD, I was a little bit, wondering what kind of topics I should present, because, practical QKD covers many important topics relating from finite key security all the way to, even experimental countermeasures of side channel. So in this tutorial, I try to stay true to my form that I'm a theorist, not really an experimentalist yet. Is that I'll introduce the basic tools of the finite key security of QKD, covering very high level concepts and eventually migrating towards the security of imperfect transmitter for QKD. So let me see, go to the next slide. So, I think we can all agree that the security of practical QKD is an area of active research in the community. And in this talk, as I said before, I will focus on the finite key security, some high level concepts, and some of the latest results, related to, a side channel analysis related to transmitter and modulators as well. So there will be a flow of the presentation. Right, and after talking about the finite key security, the basic tools and the concepts, I would end, or rather I will conclude with a simple example that's related to the BBM92 QKD protocol to show, the younger researchers in this field, how would one actually quantify the security bounds and how to relate those bounds to the security parameters of the protocol, as well as, the various parameters related to protocol and the channel parameters. Then we will talk about an emerging field, or rather emerging topic in QKD, is that people have now started using numerical methods to bound the security of QKD in assuming collective attacks. And this is a very nice topic today, because it allows you to explore very exotic protocols that usually not that one normally cannot analyze in using traditional tools, and you would see that
Charles, I'm sorry, can I interrupt you just 1 second? Are you in your very first slide, or are you supposed to have moved to your I think
I move on to the next slide.
So we're stuck into your first slide. Actually, we're still stuck into your first slide.
Maybe I'll just go. Can you see this?
Yes, we can see.
Okay, maybe I'll just stick to this. I think the Adobe is not working very well. So you can see this slide, right?
Yes, we can see the slide called Context and Motivation.
Okay, very good. Okay. So previously you were only able to see the cover page.
Exactly. Yes. Okay. Sorry for the interruption. Go ahead.
No problem. It's a good one. Yeah. Okay. So as you can now see, this is the tutorial topics for today, and I'll go through them one by one. So if you have any questions, please feel free to raise them, and then Eleni will push them towards me. Okay, so what is QKD? In brief, it's really a method to exchange cryptographic keys between two remote sites, which are connected by a pair of channel, an authenticated classical channel and also an insecure quantum channel. So at a very high level, this is what you can imagine. You have some pre-shared entangled, or maybe just bipartite state for the moment, it's row AB, right? And you're limited to it, let's say you only can do local quantum operations, And once you're done with the local operations, you can then perform your classical operations, with your classical communication on top of it, right? And as one could imagine, this can be seen as a LOCC map that takes the initial, bipartite state shared between Alice and Bob and maps it to some classical state, which will consist of the output keys that you're going after, as well as the overhead that you would have generated using the classical algorithms that you will use to process the key, including error correction, privacy amplification, and so on and so forth. So one of the things that we would allow the adversary to have is that she can hold the purification of this row AB, and at the moment, row AB can be seen as the entire sequence of quantum signals or quantum system being held by Alice and Bob, right? I'm not yet talking about the size, so you can take it as a generic state owned between Alice and Bob, and this, of course, account for general attacks, right? So let us put a bit more specifics into the protocol proper, or the definition proper, right? So here we assume that K and K prime, Alice and Bob output keys respectively, right, can take value from some L bit string, right, which is determined by this pool here. And then you also need to consider the case where, Alice and Bob would also be able to produce an abort signal, right? And this would typically mean that the protocol has failed. And this failure can happen due to many reasons. One of them could be because your error verification has failed, the Alice and Bob don't end up with the correct key after error correction, or during the parameter estimation phase, in which Alice and Bob realize that the error is too high, and then they abort the protocol and they restart again. So the output state, when you apply the generic map or the QKD map to the purified state owned between Alice, Bob, and Eve, this is the state which they will own at the end of the day. And what is different from before is that you see that the classical registers being held by Alice and Bob, right, they could be entangled or they could be correlated with Eve quantum site information. And we define this state using equation 1. And the key point here is that you can see it's a combination of two parts. One part will consist of the term in which the system aborts, right? And in this case, it's a very trivial outcome, and we just assign an abort signal to both Alice and Bob key output, right? And then we attach some auxiliary state to the adversary. On the right-hand side, which is the below state, is the state of interest to us, right? Because this is the non-trivial output, and we would like to characterize, how likely the two keys are identical, and as well as how independent the state is from Eve quantum site information. So this is the generic state that one could write down in terms of modeling the output of a QKD protocol, right? And this protocol, or rather this description, is pretty generic and high level. Yeah. So we also should pay attention that the output state, right, namely the non-trivial output state, is subnormalized, right? And when you take the trace over this, it should give you the probability that the protocol succeed. And this is important because, and this is also a parameter that one cannot really control in theory, but rather in practice, this is something that you should look to characterize with your system, right, in a well-controlled environment, right? And in our language, we typically refer to as the robustness property of the protocol. So now we've talked about the actual output of the system. The next thing to do is, of course, to define what would be an ideal output. In this case, the ideal output, again, you should allow for the setting in which you would also have a abort situation. The protocol could fail even with the ideal setting. But important thing here is that the non-trivial state is that you are looking at a product state. This product state here would mean that the adversary has completely no information about the output key, and on top of that, we also require that the output key are perfectly correlated, right? Because that's the whole point of QKD, and that's the reason why we started off, first informally defining what do we expect from a QKD protocol. And one thing is that the keys must be identical, because otherwise you will not be able to use it for symmetric encryption. And the second thing is that the key produced by both Alice and Bob, they should be independent of the adversary. And this is exactly what equation 4 and equation 5 would inform us of, right? And naturally, you would also have the case where the protocol also, will be, the state is subnormalized, and the protocol also assign the robustness probability to the non-trivial output of the protocol. Okay, so this is a security definition, and I guess most of you have seen this before. And this is a very, very well-known one. And if you want to know more about where this notation or this concept comes from, you can look into the review paper by Christopher and Renato, which recently has been updated, and it will be you can find in this archive version. So what this says is that you want to compare how distinguishable the output of the protocol is with respect to the ideal state, right? And since by definition, when it aborts, it actually produces a secure key, so you can actually simplify the criterion above in equation 7 by equation 8, right? And as you can see, now if we normalize the non-trivial output states, then what you get is that you get a prefactor which corresponds to the robustness probability. All right. And what is so nice about this criterion is that it actually allows you to take the QKD keys, right, and its security guarantee, and consider it, within a bigger cryptographic application. And even if you do that, what is so nice about it is that the error, right, doesn't increase. It is basically preserved in this framework, and you can actually compose it with other components that is within this larger cryptographic application. So the whole point of finite key analysis, right, or rather one facet of it is that we would like to establish type security bounds, right, or type bound on the security error in terms of the security parameter. So in a way, once you define what the protocol proper is in terms of its block size, its tolerated error rate, the various parameters that you could enforce from your side, right? Then you would like to say that what is the security of the protocol using the criterion we just described above. And in this case, what we have is that you can actually analyze the security of QKD using two independent parts. One is the correctness, and we already mentioned this before, that we like the two keys to be identical at the end of the day, and this correctness quantifies, right, how likely the two keys would be different, right? And this is typically referred to as the correctness criteria. And the second one would be secrecy, and this quantifies how different, maybe I should put it this way, is that how secure the output key is with respect to some reference states. And this reference states, again, tells us, it is looking at a uniformly distributed state, and then it's independent of the information, all right? And what is really nice is that, if you have a protocol that is guaranteed to be, let's say, epsilon correctness and also epsilon secret, then when you combine these two features together, you actually get back a protocol that is based on the previous definition, equation 7, that is epsilon correct plus epsilon secret secure, right? And this is very nice. And basically, this is telling you that you can analyze the secrecy and the correctness of the protocol independently, right? And guaranteeing and trying to ensure these two conditions are met would naturally tell you that your QKD protocol is the sum of these two errors secure. So moving on, the most important part of finite key analysis is to really list down the various errors that's related to the classical post-processing layer. So you recall earlier on when I talked about having a LOCC map, and part of the LOCC map would correspond to performing error correction, privacy amplification on your measurement data, right? So you can imagine that the CPP layer consists of the following. Step one is the parameter estimation. And in this parameter estimation step, you actually have this thing called a sampling error. And later you will see in more details later on, is that the sampling error looks at the case where your parameter estimation has failed in doing its job. And I will define more clearly what is doing its job. What does it mean by doing its job correctly, right? The next thing will be error correction and verification. And here what it does, you need to correct for the errors in the measurement outcome, right? So that Alice and Bob would end up with the correct keys. And even though you do perform error correction, there's a small chance that the two keys are not corrected properly. And what people normally do in practice is that they apply hashing to it to check, to ensure that the two corrected strings are equal or identical with very high probability. And in the case where you actually have different keys, but your hashing values are identical, then this is what we refer to as the collision probability or the hash error. And again, this is something that you have to take into account when you compute the finite key security of your protocol. And finally, coming to privacy amplification, here we talk about approximate security. That means when you use, for instance, a randomness extractor to extract out all of the randomness that you have in your weakly random source, then typically, to optimize the randomness extractor, people will look at the case where you allow some error in the output in the sense of the statistical distance to some ideal state. And this I will again come back in more details later on, right? So, but in brief, the whole point of this exercise, is that to tell you that the errors that arise from all these various steps, they are actually from the non-asymptotic or the finite key analysis of the individual algorithms. And you can actually make them extremely small if you have a sufficiently large data size to play with. So that's a kind of a trade-off. And the whole goal for us is that, you want to maximize the total key length, the extractable key length that you can have by optimizing over these errors. And the errors are typically fixed. And you have some freedom in designing the protocol in that sense. So let's move on to parameter estimation. So here, the whole goal is to say that, when you have a raw key that you generate from your measurement data after sifting, right, you would like to infer the error rate in the final key that you use for distillation by taking some random sample from this pool. And this can be seen, it can be broken down into a very simple problem, which is based on random sampling without replacement. So here, what you have is that you can consider a binary sequence of n bits, right? And this n bits will just simply correspond to the error position in the raw key pair. So these are realized values. These are not random variables. And then what you do is that you will draw k positions out of this n length sequence, right, without replacement. And this will form your random sample, which in practice typically people refer to as the sample that you use for parameter estimation. And the goal here is to say that when you take this random sample, you want to infer how many errors there are in the remaining sequence, right? Which is of course given by a size of small n, which is just the difference between the capital N and the k value, right, that you sample from. And so what we're looking at here, what events are we looking at, is that this is the probability of interest for us, right? And in this case, you need to first define what is the tolerated error rate, and also, what kind of deviation gap you're interested in and you're comfortable with at the end of the day. And in equation 11, you should be able to identify that this corresponds to the average error rate of the random sample, and this would be the remaining error rate in the final key that you'll be using for your error correction and as well as your privacy amplification. So if you scrutinize this carefully, this will simply mean that, on the left-hand side, this is an event that corresponds, telling you that your random sample, when you draw it out without replacement, the error rate will be less than some predefined tolerated error, right, which is denoted by delta here. And simultaneously, you have the event that the remaining error, right, in the remaining sequence is actually greater than the tolerated error plus some margin or the deviation term that you allow. And this is clearly a bad scenario, because the whole point of parameter estimation is to say that, if your protocol is to produce a random sample done through the parameter estimation phase that has a small enough error rate, then with very high probability, right, the remaining sequence should contain the same error rate or lower than that, right? And that's the whole purpose of parameter estimation. So this event as defined here would be a bad event, and our goal is to put a good bound on this, right? And this bound should be given by an exponential bound. So in the work that we did with Marco Thomas Michel, Nicolas Gizon, and Renato Reiner back in 2012, what we did is that we actually established a pretty good bound on this event, right? Using the Surfling inequality. And this inequality has a very nice feature that is actually independent of the total population error, which is typically not a situation that's being considered in the usual statistical analysis domain, right? And no, because this inequality proposed by Surfling is pretty generic, like the Hoeffding inequality, it also applies to also non-binary valued sequences as well. And because of that, you can imagine that this kind of analysis, although it's good for certain region or regime of the parameters that we're interested in, but it's generally not tight, right? So of course, when you talk about finite key analysis, one of the main subjects is really to put very good bounds on the error related to a bad event of parameter estimation. And one thing maybe some of you have already noted is that when you do random sampling without replacement from a given pool of data, right? This distribution of errors is actually given by a hypergeometric distribution. So if you want is to make use of this information and build up a exponential bound, you can effectively, or rather get a sharper bound in certain regime of interest to the finite key analysis of QKD. And what we've found in the recent work is that you can actually do that by tapping on the Schroff and Strover hypergeometric inequality. And the trick here again is that, in all of this hypergeometric inequality or concentration bound is that they always assume that, the sampler always have access to the population parameter. But in this case, because we're dealing with QKD systems, we don't have access to the total error rate as part of the measurement data, right? So you need to find ways to get rid of that constraint. And that's what we did in this work. So I would also, encourage the younger audience to look into tightening these bounds if you're interested in this topic. And there are a few, directions which I thought would be useful is to look at, some of the new concentration inequalities being developed by other domains of our field. For instance, the one by John Daniel will be related to the parameter estimation of the Bell violation, right? And as well as Ying and Chen, who recently proposed some new bounds. But I think it takes some work to be able to adapt it to the bad events that we just defined. But it's an area of course, interest to those who are looking into this area. Okay, so let's move on to privacy amplification. So here, the rough goal is
Charles, can I interrupt you 1 second before you move on to privacy amplification? Since there is a question on error correction, and I think it would be nice maybe to group it right before. Can I relay it so that maybe you can answer it? It's from Adomas Baliuka, and it's about error correction. So he's saying, when using standard error correction methods, the failure probability can be correlated with the keys and the error pattern. Thus, the event error correction success may give a small amount of information to Eve. However, the failure probability only seems to play a role when we require that the protocol only needs to be secure in case of success. So here is the question: how is the success information accounted for? As a simplistic example, what is stopping one from using an error correction that sends no bits over the classical channel and just guesses all zeros as the key?
Okay, so typically we have a way to quantify how much information is being leaked for specific error correction code that we use. And in our modeling, we have this efficiency prefactor that we assume in a very simplistic modeling. But in practice, you just have to, how much you disclose about your key through the error correction algorithm, you would have to account for that in your privacy amplification, right? That would be the first part of the answer to the guy who was asking it. And the second part would be, when you do verification, the leakage that's due to the verification would also be taken into account for privacy amplification, and this would be seen later on.
Very good. Yeah. Okay. Thank you. I think that answers the question, but Adomas will ask if you need more explanation. Thanks.
Okay. Yeah. So let's return back to privacy amplification. So this is already the heart of the finite key analysis of QKD. You will see why later on, right? So the whole goal here is that when you're given some raw key, right, or some random source, right, and we assume that it could be correlated to some adversary, right, with some information E. And the whole goal here is that when you have access to some very small random seed, you can apply what we call as a randomness extractor. In this case, the definition will be we have to use one that's quantum proof because we want the final output string to be also independent of the adversary, and also it has to be a strong extractor in the sense that it also has to be independent of the random seed that you use to randomly choose the extractor when you apply to the raw key, right? And this is a definition that we have when you define with respect to a quantum adversary, right? If you look into the definition carefully, you will see that all definitions of randomness extractor actually requires you to have some guarantee. And indeed, this has to be the case because if you have no guarantee on the amount of correlation the adversary might have about your raw key, then it's impossible to do extraction, right? That will fulfill this condition here. So for the purpose of randomness extraction, what people normally do is that they need this guarantee that the mean entropy of X given E has to be at least greater than some k bits, right? But this is just a definition. Later we will show you what are some of the major results in this domain that allows you to construct a realistic quantum-proof strong extractor. Okay, so there are essentially 2 points in this section. One is that 2 universal hashing is in fact optimal and can be used to construct quantum-proof strong extractors, and optimal in the sense that it can reach the maximum output length that is defined by some fundamental bounds, right? And the second thing is that if you want is to consider smoothing of the mean entropy, then actually it gives you the optimal rate of extraction as well, right? And if you look at some of the converse bounds in this domain and in this field, you will see that actually the smooth mean entropy is the right quantity to use and also the optimal quantity to use. So now I'm just going to state a result from Renato, and what he says here in his results, and also being extended later on by Marco Thomas Michel to different families of universal hashing. Here, one could see that you just let rho xe be your classical quantum state as before, right? It could be correlated with the adversary using the mean entropy characterization. But here, what the theorem says, or the lemma says, is that if you were to randomly pick a function from a family of universal hash families, hash functions, then this is the guarantee that you have, right? That the statistical distance between your output state and some ideal state, right, that you are going after. So this ideal state here, if you look at it carefully, this is a uniformly distributed state over the output key space. This is the random seed that you have, and this is the adversary information. So if you were to apply this extractor onto your weakly random source, this is the guarantee that you will have, right? And what this means is that you have to pick the correct output length, because this is the condition that you have to fulfill based on this lemma, right? And by choosing the right length, as you could see in this left-hand side of the slide, then this will naturally guarantee that your secrecy is upper bounded by epsilon 1 plus epsilon 2, right? Where the epsilon 1 is due to the smoothing and epsilon 2 is due to the entropy loss of the extractor, right? So this is how one would usually pick the how much bits you should generate in a QKD system. You typically has to follow your analysis like this. So if you look at it, at the end of the day, when you compare the secrecy criterion we just introduced for QKD and also the leftover hash lemma in the presence of quantum site information, you would see that if you pick epsilon 1, epsilon 2 such that it fulfills the security that you require, and if the smooth mean entropy of X given T is the transcript that you would disclose during the classical communication stage of the QKD protocol, and E will be the site information that Eve would have acquired during the quantum communication phase, right? What you need is to basically fill in this blank, right? Once you know this information, then you can go on to design your key distillation engine, right? But generally, this quantity is not so easy to lower bound, right? But there are 2 broad approaches. One I would say is based on information theoretic approach, and this is largely created by the branch from Renato Rana. And the other one would be based on entanglement distillation approach, where one uses concepts from quantum error correction codes, to decouple between the bit error and the phase error, so that you can apply it through what we usually term as the Shaw-Press QCrypt. And I will use that later on, in fact, when I talk about the QKD transmitter, about the security QKD transmitter. Okay, and what's interesting, you can see the poster by Surumaru, I think it's poster 67. And what he actually has shown is that, these 2 approaches, although, some people use this branch of analysis and another group of people use the one based on entanglement distillation, but essentially, in terms of, characterizing the error or the security of the protocol, actually, that's just a constant prefactor in between these 2 approaches. So there's not much difference between these 2. And essentially, once you have proven one approach, it says the same for the other one as well. Right. So, then it becomes a question, how do you compute this term, right? A lower bound on the smooth mean entropy of the classical quantum state of interest here. And you might say that, let's compute it directly based on the definition of smooth mean entropy. Let's just try to characterize the entire family of bipartite states that are compatible with your measurement statistics. But actually, it turns out, if you were to do that kind of characterization, it's just not feasible in practice, right? So, but what is nice is that it's been observed in the field that it's sufficient to consider security against collective attacks, right? In the asymptotic limit. But what we're after here is actually not the asymptotic limit. We're looking at the finite key security of QKD. So this observation is not exactly watertight when you consider finite, key sizes, but pretty good proof strategies actually exist, and I'll just go through some of them for concreteness. So the most recent one that to the best of my knowledge, right, is one that allows you to directly bound this movement entropy, and this is what is based on a technique that is called entropic uncertainty relations, right? And using this technique, people have found ways to bound directly this movement entropy of protocols that is related to discrete variable, decoy state, as well as continuous variable system as well, right? And you can also see, in some of the talks that we have for this QCrypt edition, some of them actually make use of this technique, right? The next approach actually first, look at the bounds or the security in terms of collective attack, right? Analyzing using von Neumann entropy, and then eventually promoting that approach towards general attacks. And these are usually based on the definity theorem, started first by Renato in the case of quantum system, and then also more recently with the other colleagues that he has, they promoted it to post-selection technique, which is a lot more concise than the one based on exponential bound. Although more recently, based on entropy accumulation theorem, one can directly bound the guessing probability of the single round, using this proof technique. It's very nice because it applies also to device-independent QKD, right? In fact, you can see one of our collaborator, Ernest, he's going to talk about this, I think, later on today. So let's go through a simple example based on the entanglement-based protocol. And why I picked this is because it has gained a bit of visibility due to the mission satellite launched by the Chinese researchers. And here what we have is the BBM92 protocol. You can see that there's an entanglement source in the middle that's untrusted. And then on the Alice side, let's say on the satellite, you have a passive basis choice decoder. And on Bob's side, he has the same setup as well. Right, so there are two important assumptions here is that, even though the entanglement source is untrusted, but we actually require the measurements to be trusted, right? In fact, a squashing model is required as well to map high photon states to the single photon state so that you can still restrict the analysis to qubit protocol or 2 qubits protocol. Then we also require that the POVM elements corresponding to the inconclusive outcomes on both sides, right? Rather between the two different bases that one could have. Right, they should also be identical, and this needed to prevent attacks that's related to blinding attacks and those that would actually influence your detection probability based on the basis choice of Alice and Bob. So let us define what the protocol is, and this is going to be quite involved, but we will go through it bit by bit. So when we define a protocol, we need to define the block size, the sample size that you look at for random sampling, right? The deviation term, the syndrome size, the leakage essentially you have during error correction, the hash size, and finally the output key length, right? And it's denoted by the symbol L here. So for the measurement phase, you can imagine Alice and Bob, they first agree on a random binary string, right, of length m because the total block size is m, and then they perform authentication later on when they do sifting and just to determine exactly what is the final block size that they have, right? So what we're going to do is that the measurement outputs of Alice and Bob can be divided into two segments. One is the raw key, the final raw key that they will have for key distillation, and V will be the part of Alice that she'll use for parameter estimation. And likewise for Bob, we denote Y for his final raw key and W for his random sample, right? And that's where they will do parameter estimation as we discussed earlier on, is that Alice would send a part of, will send the V portion to Bob, who would then compute the error rate between his part of the string, which is W, and V, right? Using this formula, they just compare the Hamming distance between the two strings, right? And if the error rate exceeds tolerated error, delta, then they abort. Otherwise, they proceed to the next step. Then at this point, they will do error correction because they have already agreed that there's a sufficiently low error in their final raw key pair. So what they do is they perform one-way error correction, whereby Alice would send a syndrome of length R to Bob, and then Bob would, based on this syndrome, recover back Alice key, right? Hopefully it recovers back Alice key. And once they're done with that, they will then perform a hash on each of the portion that they have. And then they compare if the hash are different, they will abort if they're the same, then they proceed on to the next stage, which is privacy amplification based on doing universal hashing, which I just introduced earlier on, right? So once you have that, once we define the protocol, you can clearly define what are your error rates, right, for individual segment. So what we have here, you can say that the protocol is actually epsilon QKD secure, right? If there exists some free parameter that you can choose, that this constraint equation 16 is satisfied, right? And you can identify that this is due to the verification error, and this is simply just your collision error due to using a universal hash function, right? And the other two terms, one is due to parameter estimation, and this one is due to privacy amplification, right? And these are the error rates or the error functions related to these two algorithms as defined. Okay, so you can look into the paper for more details, but this is the essential idea here, right? Is that we can define the total error of the QKD protocol in terms of the system parameters and the channel parameters that you would require. So one important note here is that this error function that we have for the parameter estimation is based on the earlier result on surfing inequality, right? And as I would show later on, you can actually improve it quite dramatically using the one based on Harsh and Schofer inequality for hypergeometric distribution. So how do you optimize the key rate? So this is the algorithm that you use, is that you would like to maximize the key length, right? And you can actually characterize the key length in terms of some ratio alpha. And alpha here is what normally people will refer to as the secret key rate. And the definition for this is that it's just a number of extractable secret bits they can have divided by the total block size that you define as the protocol parameter, right? So these are the constraints that we have. The first line, you will be able to recognize that this is the security condition that we require from the theorem that we just introduced earlier on. And the rest are the free parameters related to the protocol proper, right? And for the purpose of this simulation, I think the earlier participant was asking, right? And here what we're doing is that we actually model the leakage using a very simplistic model where there's the error correction efficiency of 1.19 multiplied by simply the error that you have in the final raw key. Okay, so defining the optimization program like this is one thing, but you still need to fit in some of the channel parameters, right? And what is a good way is that you just simply take some of the experimental parameter that you have from, let's say, a recent experiment, and you plug into this program and you see what you get. And this is what we did using the recent Meteor satellite, which is based on this BPM92 entanglement-based QKD using passive basis choice. So you could see here it's a plot for various bounds. You would just have to focus on the solid line, right? The solid line will correspond to the error function that's based on the new hypergeometric inequality. And the red line simply refers to the block length that is gathered by the Meteor satellite. And what this says is that there is a limit, or rather a minimum error that you can expect of the QKD protocol, right? If you were to choose an error that is too stringent, like in the case where it's 1e minus 10, then what's going to happen is that this is the amount of secret key that you can generate in general, right? And you need a significantly larger block size. But if you were to relax the error and say that I consider, let's say, 1 in a million part that it will fail, then you might be able to generate more keys, right? So in short, what you have here is a very delicate balance between the extractable key length, and the security error of the protocol based on the parameters that you set in practice, right? So this is just one example. Yeah, so let me move on to the second part, which is about the numerical methods for QKD, right? So why is numerical methods so useful? Early on, I mentioned that it allows you to explore quite exotic protocols, but going back one step is that although we have direct bounds on the smooth mean entropy in the finite key regime, but actually there are also very good bounds, right, that allows you to consider collective attack first and then promote it to general attack. So in this case, it actually makes sense, for people to dive and try to characterize tight bounds on the single round entropy, and this typically measured by the conditional von Neumann entropy of X given E. So there are a few recent results and largely generated by a Norbert Luckenhaus group So what they have developed is a very nice numerical techniques that allow you to apply to a wide range of QKD protocols, but under the assumptions that the device are trusted, right? And you can see that there's a new, more efficient algorithm that is being introduced by who. You can see it's poster 216, I think, right? And more recently, our group, in collaboration with some of the international collaborators, is that we managed to extend this kind of ideas to the case where you can have one-sided device independent setting, and also as well as to measurement device independent MDI QKD. And in this case, what William has done is that he's extended this to a very versatile framework, which I'll introduce later on. And this allows you to look into MDI QKD with coherent states and also with Trojan horse attacks. And Eli essentially extended this result to mixed state as well. Okay. Then even more recently, actually, there are two branches now, or rather two parallel efforts. One is from Peter Brown and Fuzzy, that they actually found very nice way to lower bound the conditional mean entropy, the conditional Bonner entropy of X given E, right, in the device independent setting. And that's what we have done as well. And I think Ernest will also talk about this later on, right? You can look at the presentation by Peter Brown. I think it's 3A, talk number 3. Okay, let me quickly move on to MDI. So in the MDI QKD context, right, you can actually first consider the actual protocol. The actual protocol will be, you have Alice and Bob, right, which will produce independent quantum signal. They'll send it to a central hub, typically we refer to as Charlie, who will make a joint measurement or Bell state measurement ideally, right? And then it will produce an outcome Z, and it will announce to Alice and Bob, right? And Alice and Bob, based on this outcome, they will either do a bit flip to get back to the corrected state, and then based on this, they estimate the virtual state that they have, is it entangled or not? All right, and this is what we mean by entangled is through this virtual protocol, that you can also imagine virtually that Alice and Bob they initially created some pre-share entanglement between in their own individual sites. Then each of them send one half of it to Eve, who then make a measurement. And once she has made a joint measurement, she announced the outcome, announced it to Alice and Bob. Based on this outcome, Alice and Bob would then rotate the state accordingly. So this is essentially entanglement swapping, right? And in this case, if indeed everything proceeds as in the ideal case, then Alice and Bob should end up with a maximally entangled state, right? So when you look at it this way, it turns out that MDI QKD protocol, even though they use prepare measure setting, you can actually always map it to an entanglement-based picture, and you can proceed with the analysis as per usual. Okay, so here I'm going to go through some of the machinery introduced by William and our group. Is that you can now imagine that Alice and Bob to prepare some states is denoted by this symbol, right, or these notations. So they can be anything. They can be qubit states, they can be coherent state. They just have to be pure states in this case. Right, and because they are pure state, you can always imagine that you can view the quantum channel and the measurement collectively as a quantum to classical mapping. And this is the most generic formulation one could have, within the realm of quantum information theory, right? So this would then consist of Eve site information, right? And this will be the measurement outcome that she would have to announce to Alice and Bob. So the key idea of this approach is that, the Eve site information, which is a collection of pure states, they actually form what we call as a gram matrix. And this gram matrix, certain entries are constrained by the expected channel parameters, and as well as the inner product information of the encoding state. So if you look at it, this equation 18 is just one row of it, right, or one entry of it, is that you see that Eve inner product information is tightly related to both Alice and Bob inner product information, right? And this means that, how you pick your state, your encoding state, whether how non-orthogonal they would have some influence on Eve site information. So beyond this, apart from the inner product of Alice and Bob encoding state, you can also imagine, imposing more constraint based on items or rather elements like, detection probabilities, right? And this is what you could do based on this equation here, is that the probability of success for a given basis also is related to the inner product of the Eve site information. And likewise, for the bit error rate as well, you can use Bayes' rule to relate in the same fashion, right? Eve gram matrix information. So now, because we're looking at the asymptotic, limit, you can actually consider the typical Shaw-Press QCrypt. And here on the left-hand side, this is due to the privacy amplification analysis, and on the right-hand side is due to the error correction leakage. Because it's in the asymptotic limit, what you have here is that all those terms like the error functions, all this, they will all tend to zero. Right? In this case, so you just have to focus on the von Neumann characterization of the key rate. So typically the bit error is fixed because it's part of your protocol definition. But the one thing that you cannot fix is actually the phase error rate, right? In fact, it's a hypothetical parameter because you cannot observe it in practice. It needs to be optimized given the constraint that you have set for the protocol and also the channel parameters. And this can be done using semi-definite programming as per this program that I just shown here. Okay, if you were to run this, then essentially what you get is a very versatile framework, right? That allows you to relate the inner product, the encoding state, and it can be, in fact, any kind of input states. It can be coherent states or any high-dimensional quantum states as well, including any modeling of side channel signal that you have, right? And naturally, what we get is that you are able to use this method to analyze a large family of transmitter side channel or even noise problem. Right, for mixed state MDI QKD, I already told you that there's a nice result by Eli, and more recently, what we can show is that you can also look at coherent state MDI QKD that is secure against arbitrary Trojan horse attacks, which I'll show you later on. And for discrete phase randomization recently, also there have been efforts that look at the case where you don't actually fully randomize the phase of your signal, but you only look at some discrete finite discretization of the coherent state, right, that you have. And indeed, people have used our method to also look at the security of twin field QKD in this direction as well. And more recently, I think Eli and Hai Guang, they also extended our result to the case where you actually can have a passive time-dependent source side channel. So beyond this approach, of ours, which allows one to look into various very realistic, side channel issues related to the transmitter, there are also nice complementary approach coming in from essentially Marcus Curtis' group, which looks into this technique called reference technique, which is very nice. It looks at the probability that you can assign to an ideal state and the actual state itself, and then based on that, put an upper bound on the phase error rate. Right, and they have some very nice results, so I encourage you to look at the poster that they have. Okay, so I'll just run you through how we can actually compute security against any sort of Trojan horse states that Eve can imagine, right? Based on the technique that we have. So a generic Trojan horse state can be written in this form, right? And this is an entangled state that looks at the photon number state that Eve injects into Alice and Bob system that could be entangled with an, let's say, an ancillary state of the adversary of Eve. Then you should note that this formula, right, actually looks at the case where Trojan horse are actually mixed itself, because if you trace out Eve information, then what you get is a mixed state, given by this formula. And if you were to consider phase encoding MDI QKD, then what you have is that the output Trojan horse state, after going through the transmitter Alice and Bob, would acquire this phase information, right? And this will be the eventual Trojan horse state that you can attach to the analysis that I've shown you earlier on. So more concretely, this is what you get, right? That you look at the overall state, which I early on already introduced to you, that is to be a pure state. So this will be the cluster state prepared by Alice and Bob. And this will be the generic Trojan horse state that I just defined earlier on. And again, you walk through the same machinery as before, and then you can also map it to a set of quantum state information owned by the adversary that is also pure, right? And obviously, these Trojan horse states, they cannot be any Trojan horse states, right? They have to be bounded by some energy bound. So this energy bound is what we define as a new bound here. And there are a few ways to go around implementing this threshold in practice. One is to base on this laser-induced damage threshold proposed by Luca-Marini and colleagues from Toshiba in 2015. The other one is to look into one of the passive device that we recently proposed in our group that is based on thermo-optical defocusing effects. All right. So moving on. So this is the the MDI QKD experiment or the implementation that you can imagine here based on phase encoding, right? So you have Alice and Bob, which does only a single PM to modulate the signal. And you have the installation of power limiter, which will then characterize what is the energy bound that you can have in your analysis. And as you can see in the asymptotic analysis that we did on the left-hand side, you have your key rate based on APD, right? These are 10% efficiency detectors with pretty high duck count rates. And on the right-hand side, you have it with SNSPD type detectors, which gives you very high detection efficiency. In this case, 85%, and the bit error, the duck count rate is actually pretty low, 2 order of magnitude below your standard APD detectors. Okay. Yeah. So, to conclude, there are a few open problems that, I will encourage the younger colleagues to look into. One is actually the numerical methods for finite key analysis. So before, people always use, rather look at numerical methods that put lower bound on the single round entropy, and this is the asymptotic quantity. Would there be ways to directly evaluate the smooth mean entropy of a given protocol, right, using numerical methods? So there's some progress in this area. You should look at this paper listed here. And also, well, more for practical reasons, is that a lot of us, we always start off the assumption that the classical channel is completely authenticated and it comes for free. But in practice, if you want to calculate, the overall key that you can generate from a given QKD system, you also have to look into the cost of the authentication and the security of the authentication scheme as well, right? And this is what I would term as the finite key security of practical quantum key expansion rather than key distribution. Then one thing that is still missing is the finite key security of QKD with two-way classical communications. Largely, if one is to use, let's say, Cascade in your error correction code, then these are two-way interactive protocols, right? And how do you quantify the security of this kind of two-way interactive protocols in the finite key regime? This is also something that is still missing in the domain. And the other interesting bit would be to combine discrete variable QKD, let's say the transmitter side, with continuous variable QKD based on homodyne detection. And you can look at Qi Ping's invited talk, I think it's on Wednesday, Central European Time, 4 p.m. And that's where he combined both ideas. And then it's nice because then you can, release the disadvantage of DB QKD, which is very expensive detectors, compared to one where you use a homodyne detector that can be significantly cheaper, right? And one of the questions that I always have, and many industry partners have also asked me, is that how do you decide what is the epsilon in the QKD system? And it is an open question, and I hope this is a question that people working on standards will address this in the short term. And I'm sure you have some ideas as well, and very good ideas. And I look forward to seeing your work in this current QCrypt and the future QCrypt. Yeah, so thank you very much for your attention. I think I'm at the end of my presentation.
Thank you very much, Charles, for this nice presentation and tutorial. So maybe what we can do to start the question session is go back to the first question you had, because I see in the Slack channel that the person who asked it was not quite happy with the answer. I mean, it wasn't enough for them. So maybe I'll let Adomas speak. So let me see how the don't know.
Okay, sorry, can you hear me? I haven't tested my microphone actually.
Yes,
okay.
we can hear
you. My question was, in this finite size, for example, I've been looking at the papers by Lim and Ruska, for example, for finite size in BB84, for example, and with decoy states. And the same formula that you showed in your talk, which is that the security only depends on the failure probability, in the sense that the more your failure probability is, the more secure you get, because you only need to be secure if you succeed. However, my example is somehow this framework has to exclude this very stupid error correction method, which sends no syndrome bits during error correction and just guesses zeros. So this obviously leaks the entire key, because Eve knows what the method is, which means that if it succeeds, the key has to be zeros. And it doesn't transmit any information for error correction, and has failure probability almost 1. And A subsequent verification step using a hash would only subtract a constant term from the secret key length, which would not make it 0. So my question is, how, when using this stupid error correction method, does the secret key length become 0?
Yeah, so maybe I can turn around and ask you, how do you quantify the amount of information that's leaked through this stupid error correction code?
So like the naive view would be to look at the syndrome length, which is in this case would be 0. Mm-hmm. And I haven't actually seen any detailed discussion of how one would compute this beyond just looking at what is being sent over the classical channel.
Okay, so I think there might be some misunderstanding in the terms being used. I would take this offline, but maybe before I do that, I need to show you something. So you look at this optimization program, right? What you have described earlier on is to basically modify this term, right? This is the term which I use to model the leakage one would have due to error correction, and this is based on some expected bit error rate that one would have, right? And
by error rate you mean the quantum bit error rate in this case, right?
Yes, in the final raw keypad that you would use for privacy amplification.
Yeah. So in your paper, instead of this term with like efficiency and entropy, you actually have the length of the syndrome in the formula, if I understand correctly.
Correct. This is purely for simulation purposes to understand, how the protocol would perform in a realistic setting. But in an actual implementation, one should really look to using the total number of bits that you exchange for the error correction part.
Okay, so in my example, this length is 0.
Yeah, so there is something wrong in your argument, or something that is not correct, and we will take this offline. Yeah, then go into more details.
Okay, thank you.
Sounds good. Thanks, Charles. There was also a request from Vardan Monke. If you could please explain privacy amplification intuitively. How can somebody understand privacy amplification intuitively?
Intuitively?
Can you say a few words about that?
Yeah, let me go back to that slide. I think this figure is very nice. So the important thing in privacy amplification is actually this quantity, the mean entropy of X given some site information E. So this guarantee actually tells you that there's some randomness, very high level randomness that you have in your weakly random source. And if you were to fulfill this condition, then you can apply an extractor. An extractor is like a random function seeded by a random seed that allows you to pull out all of the randomness that you have, right, with respect to some site information E. So I think it's pretty intuitive, at least for me, that if you were to use a randomized extractor, then the mean entropy definition or the characterization would be sufficient.
Okay. Thanks, Charles. So I do not see any other questions. Okay, says Vardan. Okay, so I do not see any other questions in the Slack channel. I have a couple of questions, several actually. I'll try to limit, but since we have a little bit of time, so I wanted to ask you, Charles, what is your can you tell us a few things about some other practical QKD protocols, a security analysis for those protocols, for example, that are based on differential phase between pulse? I'm thinking of coherent one-way or the DPS QKD protocol. Can you say us a few words about the security analysis of such protocols?
So, as Elaine, actually, this is a very good question because, distributed phase protocols traditionally has been very hard to analyze using the standard tools that we have, because the standard tools that we have, they're essentially very well designed for specific qubit. You define what's a qubit signal, you define what's the encoded state, and then from there you can break it down into collective attacks and then start it from there. But for distributed phase, you always look at statistics between adjacent signal, and because of that, you cannot apply the traditional tools. I would say these are very practical protocols because they are not only based on coherent states, but they actually make use of the information that you have between neighboring states. As you can imagine, in fact, a lot of the earlier work in this topic, they first project a block of this signal, right, into some definite photon number states, and then from there they apply the usual short-Praskew analysis. right? But more recently, I would say this kind of approach is very good in getting a lower bound based on certain assumptions about channel. But if you were to consider general attacks, then there are evidences showing that even CAL protocol or even DPS protocol might not be as robust as one thought, right? So I would say it's one thing to be designing protocol and another thing to be designing protocol that are robust, not only in practice but also comes with very good security. Yeah, so it's not a very easy task there.
Okay, thanks. Yeah. And another question that we have talked about several times with another security expert, Anthony. So my question on this was is a little bit linked to the last question that you have put in your outlook, in your last slide. What is a good choice of epsilon QKD? For me, another related thing is there a protocol for which we can actually, with a real experiment, calculate precisely the epsilon that is needed for the security without making too many simplifications? So the general idea, I think, it is that in the end there is still, despite all the efforts that you have been describing and all this progress in security proofs, there is a gap that is persistent between theoretical security proofs and practical implementations, and it seems to not very easy to make to be able precisely. So I'm wondering, do you think that it will be possible at some point, or will we always need to make assumptions, too simplified assumptions?
So I think you already stated it, right? It's just impossible for one to describe exactly a model for practical system, because a practical system just contains too many degrees of freedom to be characterized in a reasonable way, right? So in a sense, that will always be a case where we need to make some assumptions about the device model, and in return, of course, you get pretty good rates, right? The other extreme point would be, just look at device independent QKD. But even in that setting, there are certain assumptions that you have to take care of, right? So that you don't actually lose the composable security guarantee. Yeah. So I would say this is quantum information, right? In a sense. And also crypto, because the best you can do is to put mathematical statements on the security guarantee, right? And you just have to pray that your assumptions and your models are being maintained and will help in the actual implementation.
Okay.
Yeah.
Okay. Very good. Okay. So are there any other questions from the panelists and from the audience? I do not see something in the Slack. Okay, so if there are no more questions, I think we can thank Charles again for the nice presentation and the tutorial, and we'll close the session. Thank you very much. And I will urge everyone who wants to meet you to come to the Meet the Speaker room, right? Yes. Okay. Thank you. Bye-bye. Bye-bye.